Hello, everyone, and thank you for joining us for today's session. My name is Danny, and I'm the event planner for the New York Reactor. Before we begin, please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional, and on topic. Useful links will be shared in the chat. This session is recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. It will run for approximately 1 hour with times for questions throughout. I will now turn it over to our speakers for introductions.
Hey everyone, this is Steve from the App Innovation Global Black Belt team. Glad to be here with you all today. It's brutal hot here in Brooklyn, New York. That's where I'm based out of. I imagine it's pretty hot where most of you are today, but I think most of us should hopefully be inside, sitting comfortably in some air conditioning and ready to do a little bit of learning. We're going to spend a bit of time today looking at a kind of lab walkthrough of KEDA, the Kubernetes Event-Driven Autoscaler, as well as Node Auto Provisioner, which some of you may know as Karpenter in the open source community. And we'll look at how AKS handles that and how you can use that within the AKS context. So with that, I think we're ready to kind of jump into it. We're going to keep it nice and casual and throw some comments in the chat. I'll try to keep up with questions. If there's other people who have answers to questions in the chat, any of my peers, and by all means, feel free to jump in on anything that I missed in the chat, but I'll try to keep up as best I can. All right, so I'm gonna jump over and let's start running through the lab. So there is a lab link here. You get a tiny URL /AKS KEDA NAP. I'll leave that up for a second. I'll also show the kind of proper URL of the site in a second, but let me just let this sit here for a minute. All right, I'll also kind of move in here. This is the AKS Labs site. This is something that the AKS team's been working on for a little while here. There's a lot of really awesome content. We'll kind of click around through some of this content as we're waiting for other things to happen within the lab, but definitely a ton of new interesting stuff happening here. It's an open source lab, so if you have something you'd like to contribute, they're always looking for people to share. And if there's issues that you see, please raise issues through the open source site, which you can access from the AKS Labs, and we'll try to get on top of those and get those resolved as quickly as possible. There's also an AKS blog here that you can link to. A bunch of new articles coming out. We're trying to put a lot of new and interesting content out here. I have a couple posts, and a number of my peers have put some posts out here as well. Lots of really kind of cool run-throughs and scenarios, things that might not necessarily be in kind of your standard AKS docs, things that are just kind of interesting walkthroughs of new capabilities, new previews, interesting scenarios that you might want to implement with AKS. So definitely worth taking a look at. All right. Apologies in advance for any background noise. Like I mentioned, I do live in Brooklyn, but usually it's pretty quiet. We'll see how this goes. So we're going to go into the AKS workshops here and click on the workshops link. Today, we're going to be going through, as I mentioned, KEDA and Karpenter. Those are really kind of fall into the operations space. So if you go down to operations here and click on scaling with KEDA and Karpenter, you'll be able to get to those. So let me jump in here. I'll zoom just a bit on that so you can see. So in this workshop, we're going to run through, as I mentioned, KEDA and Node Auto Provisioner. We're going to deploy a sample app, which I'll talk about a little bit in a minute. And then we're going to kind of play around with scaling that app with, we're going to use RabbitMQ as the scaler. And then we'll use Karpenter, Node Auto Provisioner, to do some node scaling based on a couple of kind of configurations that we'll apply in there. All right, so the objectives for this are, obviously, we're going to deploy an AKS cluster with KEDA and Node Auto Provisioner. In fact, why don't I, as I'm reading through this, why don't I get that started, and then we'll come back and talk about the objectives. So, set your subscription ID, account set. I've already done this myself, but clearly you want to make sure that you're on the right subscription. If you're doing dev test, make sure you're not accidentally deploying this to production to an environment that's restricted. Make sure this is a lab, this is kind of training, so make sure you're deploying it to somewhere safe. At this time, Node Auto Provisioner, which we'll be using later, is still in preview. Hopefully GA is imminent. I know the team's been working really hard on that, and I expect that we'll see that go generally available very soon, but it is at this point still in preview state, so you will have to register this preview. It's pretty quick, I think less than a minute typically when I've seen. So you kind of watch that go, And then at the end, after that's provisioned, you're going to update, re-register the provider in your subscription. So these are steps. As I'm kind of explaining the objectives, maybe jump ahead a little bit here and start getting through those. It should be pretty quick. Oh, and the last part here is you will need to go in and install the preview extension for the Azure CLI. We're going to be doing everything in the CLI. So find yourself an environment where you have the CLI. This works great in the Cloud Shell, so shell.azure.com. You can do this lab within there. There's some caveats that I'll explain when we get a little bit further on, but that's a good environment. Or if you have the CLI running locally, that's great. We are going to be doing this all in Bash, so also make sure you're in Bash. If you try to run these commands in PowerShell, you might run into some issues there. So just be careful with that. But with that, let me go ahead and we're going to start to deploy this cluster just to kind of get ahead of it, and then I'll kind of come back and explain what we're doing within this cluster creation in a minute. But let me just fire this off and just make sure this gets going, and then I'll jump back to the objectives. All right, that should be good. Okay, my resource group's creating. Make sure I don't get an error on the cluster creation, and then I'll jump back. Yeah, it looks pretty good. I think I would have gotten some sort of failure by now, but we'll check back in a second. Okay, so let's go back to the objectives, as I mentioned. So deploying a cluster, and I've already started that. We're going to enable both the KEDA managed add-on as well as the Node Auto Provisioner managed add-on. We're going to configure a KEDA scaled object, which we'll explain a little bit further, but effectively taking all of the scalars that KEDA has available to it. We're going to pick, as I mentioned, the RabbitMQ one and use that as the kind of scalar for our workload. We're going to monitor the KEDA scaling. So you'll see some commands you can use to kind of keep an eye on what KEDA is doing so you understand you can troubleshoot things a little bit better. And then we'll jump into the Node Auto Provisioner side, and we'll explain what a node class is and node claims, node pools from a KEDA perspective, and kind of show that node auto provisioning. And we'll show a bit about how you can monitor that as well. So if you're trying to diagnose, troubleshoot, or just generally see what's happening with Node Auto Provisioner, you'll get to see some of that. On the prereq side, obviously an Azure subscription, preferably one where you can have kind of full access. Obviously, in a lot of cases, environments are locked down, and it can be difficult to deploy clusters based on policies your enterprise might have. So if you have a demo environment where you can play around, that's going to make this lab a lot easier. Otherwise, as we get into it, I'll explain some of the things that you might have to modify, or kind of the key flags that you'll need to use if you want to run this within your own environment. The Azure CLI, as I mentioned, you can do that via Cloud Shell, Windows Terminal, WSL, as long as it's the Azure CLI installed into a terminal, and as long as you're using Bash, you should be good with that. We're going to be running Kubernetes CLI commands, so kubectl commands. So make sure you have that installed. That's pre-installed for you in the Cloud Shell, so you should be good over there if you're using that. And then we have a couple optional commands. I personally like using the watch command. I'm not a huge fan of the -w flag that some people use with kubectl. I don't like the way that it does output, so I tend to use watch. Totally optional. We're also going to be getting some JSON output, and I like to pipe that into JQ, which is another tool you can use to get kind of prettyfied JSON output and do a little bit of JSON path type parsing of that output. But again, those are two completely optional commands. If you want them, great. Otherwise, feel free to skip those. All right. So with that, looks like our cluster is still provisioning, which is good. No errors. So let's talk through what this environment configuration looks like. So in our case, we're going to create a resource group, which you see right here. I'm going to deploy that into EastUS2, but obviously for your purposes, if you have preferred environments, go wherever. AKS is what we call a Ring 0 service, so it should be available in all regions. So you shouldn't have any issues there. When we create the AKS cluster, and this could have been done through ARM, it could have been done through Bicep, Terraform, whatever you prefer. But for the purposes of labs, I like to do these things in the CLI. There's a couple key flags that we're enabling here. So enabling KEDA, obviously. So KEDA, Kubernetes Event-Driven Autoscaling, is available as a managed add-on in AKS. That means that we effectively manage that, or the AKS engineering team manages the versioning and upgrades and CVEs and things around those managed add-ons. So it's really one of the strong points of AKS. They have a bunch of managed add-ons. You can go, actually, we can take a look really quick. AKS managed add-ons. And we can just take a quick look at the list of managed add-ons that AKS provides, right? So KEDA, monitoring, Azure Policy, Gatekeeper, Key Vault, secrets provider. So a bunch of really cool add-ons in here. And again, they're fully managed by AKS, which is pretty unique to AKS, the way that they manage all that. The second important one here is the node provisioning mode. So auto. So node auto provisioner is node provisioning mode auto. Slightly different than the cluster autoscaler. Slightly different approach there, and we'll talk about that a little bit more. These other items down here are best practice. I don't believe any of these are actually required by node auto provisioner. In fact, we can go take a look at that because node auto provisioning. And let's look at the requirements here really quick. So I mentioned we're going to, there we go. So recommended network configurations, right? And that's what we're going to do. We're going to use the Azure CNI and overlay mode with the Cilium data plane. I don't believe those are required, but they're recommended configurations. Okay. And let's see where we are. Cluster is still provisioning. Great. Once that cluster is provisioned, we're going to get the AKS credentials there. Okay. I see a question in the chat. Is this session being recorded and available on demand? Yeah, this will be recorded and it should be available on YouTube at a later time. All right, so we'll get the credentials there. While this is running, we can go take a look at the cluster in the Azure portal. So let's jump over here. Let's refresh this. I should see my workshop resource group. There we go. Here's the cluster that's deploying. Take a look at the version. So it's going to be Kubernetes 1.31.8, CNI and overlay mode. Okay. That all looks good. All right. Once it's done, the app that we're going to deploy is going to be this pet store application. So this is a really interesting app. It's really good for demonstrating different capabilities of Kubernetes, so auto scaling capabilities. If you wanted to play around with something like a service mesh, this is great because it's multiple services. And effectively, the way it works is you have a storefront. It's a pet store. So you're going and making purchases. You have customers. In fact, we have virtual customers that we're going to be deploying as part of this. Customers are submitting orders to the order service, which ultimately puts things into a queue, which is actually a RabbitMQ queue that's running in cluster. We also have an employee site, so a store admin site, so you can look at the open orders that are there. But we also have a virtual worker. So virtual worker is taking those new orders that get sent in and then actually filling those orders through the make line service. So what we're going to play around with here is actually watching those virtual customers, scaling that up, keeping an eye on the order queue, and then auto scaling the virtual workers based on that. This also uses a MongoDB. All of this runs completely in cluster. There's some other labs out there that show using AI within this solution. We're not going to get into all that. We're really going to kind of focus specifically on virtual customers and virtual workers and this RabbitMQ. All right, cool. Looks like our cluster is now provisioned. Let me clear the screen here, and let's go and get credentials for that cluster. Again, I'm going to do my best to keep an eye on the chat here as we go. Let's get those credentials. All right, so from Jim, Steve, if you forget to create the cluster with those options, can they be added later, asking for a friend? Yeah, so you can enable after the fact, and if we go take a look at the doc, it usually does show what that would look like. So let's go and find enabling auto provisioning on an existing cluster. There you go. All right, so you can enable auto provisioning on an existing cluster. Again, just make sure you take a look at the prerequisites, the requirements, and you should be good to go. All right, cool. So we should have our cluster now. If I do kubectl cluster info, I should see there's my cluster. This all looks good. I will try not to use my alias. I just do K for kubectl. So I'll try to remember to kubectl every time. But if you see me just type K, just know that equates to kubectl. It's just muscle memory. Let's see. I don't think we have anything yet. So that's all. Shouldn't be anything. Just everything's running in kube system. But we can see here that we have the KEDA components running. What we don't see in here is any node auto provisioner stuff, really. That all runs within the control plane, so that's stuff that we won't see at our view. All right. Very cool. So we talked a bit about the app already. Let's go ahead and just get that deployed. Fortunately, the Pet Store app, you can go take a look at the site for that. If I click this link, it'll actually take us out to the site. And you can go and look at the repo. You can contribute to it. It's really just an awesome app if you want to just kind of demo or try out some capability in Kubernetes. It doesn't even need to be just an AKS. You can run this kind of anywhere. It's a completely self-contained application. So I'm going to grab this whole thing. So we're going to create a namespace, and then we're going to deploy the application with this raw link, and then we'll take a look at it all. So let's run this. All right, that looks good. So let's, again, I mentioned I like to use watch instead of -w. So let's do a watch on kubectl, single quotes. Yeah, let's look at services, deployments, and pods for the pets namespace. All right. And I believe that's also included if we scroll down here. I didn't include that. I might go back and add that command in here just so you have it. But you're really just watching the deployments here, seeing everything go. So we can see this one uses external load balancers. You could obviously, if you're running this in your own enterprise and you're blocked from creating public IPs, you can always pull down the deployment manifest and change those services to use internal load balancers. That wouldn't be an issue. The key thing that I'm waiting for right now is for this order service to come online. So there's a bunch of checks that the order service does to make sure that the MongoDB is ready, the RabbitMQ is ready. So that's what takes a little bit there. So that looks like it's running now, which is great. We did provide this command here to get the load balancer. So if I run this, where you see all I'm doing is kind of a nested kubectl get service storefront, and then I'm extracting the IP address from that and just outputting it into an HTTP. So, and this opened, of course, over here. So let me bring this over. There you go. So here's our pet store application. We can go place orders directly from here. Very cool site. We can also go in here. If I do kubectl get service for pets, I can also grab the admin URL. So let me grab that, and let's go take a look at the admin portal. And there's no orders. All right, so nothing too interesting going on there right now, but we can go back and take a look at that later if we want. All right, so KEDA. So what is KEDA? KEDA is the Kubernetes Event-Driven Autoscaler. So it's an open source project. It's been around for quite a while, very stable, been used extensively in a number of our own products, as well as with other cloud providers and out in the Kubernetes world. Very stable, very cool solution. So effectively what Kubernetes, the KEDA component does is it provides a more enhanced capability on top of the horizontal pod autoscaler. So traditionally HPA, which will, HPA is the horizontal pod autoscaler. The HPA was really focused on scaling deployments. So you have an application, you wrap that into deployment so that you can scale the number of instances of that application. You would typically use a horizontal pod autoscaler for that. The HPA would generally use CPU and memory, although metrics was added at a later time to do scaling. And it was kind of, challenging. It was CPU and memory often are not the best way to scale workloads. If you've ever kind of done a performance test of an application, it can be kind of challenging to dial in CPU and memory usage for auto scaling. Often what you really want to do, in particular in an event-based world, is scale based on the number of pending events that need to be processed. So whether that's a RabbitMQ or a service bus or something along those lines. HTTP queue depth, right? So you have requests coming in. You could scale HTTP based on the CPU, but it's better to look at, how deep is my HTTP queue? How many requests do I have waiting to respond to? That's a much better way to scale than CPU in general. Okay, so KEDA, if I jump over here, has more than 50 scalers. So you can go take a look at these. There's a ton of really cool ones, a bunch of scalers from AWS, obviously a bunch from Azure as well. There's the one that we'll be looking at further down here is the RabbitMQ scaler, but you can do something like a Splunk query, a Prometheus query, Postgres, so really powerful stuff. There's also one here that I think is really cool, which is the Kubernetes workload scaler. So this is where the case where you have one component in Kubernetes that scales, and then you say, well, based on that scaling, I also want this other component to scale. So it's kind of cool that you can build those relationships with KEDA. I think that's really nice. And then obviously cron is another really common one that people use. So you can scale based on a schedule, things like that. So very cool. I just realized I closed the chat here. So let me take a look, make sure I didn't miss anything. All right. So you should be able to, I see someone asking about enabling KEDA after the fact. You should be able to enable KEDA after the fact. I'll take a look and see if there's something that can be missing there, but you should be good to go. So how KEDA actually works, so it's an operator that you installed into your Kubernetes cluster. It doesn't have to be AKS. You can run this really anywhere. You can run it locally in K3s or something like that. But effectively what it's doing is taking these external triggers, and that's done through the scalars that we just showed, and then driving the HPA effectively. So it kind of takes control of an HPA, creates and takes control of an HPA for you, and will then scale your workloads based on that external trigger, okay? So to set up a KEDA scaler, go take a look at the docs. They have lots of good examples you can go grab. So in this case, we're going to be using the RabbitMQ scaler, as I mentioned. A couple of things we need here, the RabbitMQ host name. In this case, we're actually going to use the HTTP endpoint for RabbitMQ. You can also, there's, I think, an AMQP endpoint you can also potentially use there, but it was just kind of quick and easy to set it up this way. We'll need the RabbitMQ username and password, and then we'll use that to create a connection string. So let's go ahead and grab these and run that. Clear the screen here. Okay. Now, to save this into the scaler itself, we do need to base64 encode it. So just take a look at this command. What I'm going to do with this command is run it first. We're going to echo the connection string that we had and then pipe that through base64 encoding. And then we're going to do wrap 0 just to make sure it doesn't put any carriage returns or anything like that. So now if I go and take a look at this, so I do echo, oops. Let's clear this. Echo $. Maybe just trying to find, there we go. We should see that base64 encoded string. Now it's important to remember for those who aren't familiar, but I think most of you probably are, base64 is not encryption. It's just encoding. So don't assume that because it's base64 encoded that it's secure. There are other ways you can store this. We could put this into a something like a key vault, secret store, something like that to further secure it. But for the purposes of the lab, we're not going to do that. All right. So what we're going to do is we're going to create this scaler. So let me grab this text here, and then I'll explain as what this is actually doing. All right. Let's paste that. And then let's cat that file. To kind of show what this includes. So the first thing is that we're going to store a Kubernetes secret that has that connection string in there. We're going to reference that from a KEDA trigger authentication. So that's a common way that KEDA uses to store credentials that are used by scaled objects. And then if I look at the scaled object itself, this is what I'm going to call it, the RabbitMQ scaled object. It's in the namespace pets. The scale target reference, that's the name of the target deployment that we're going to scale. So you're always scaling a deployment. So the deployment that I'm scaling is the virtual worker, because as I mentioned, we have virtual customers that are coming in, they're placing orders. We want the virtual worker to go in and take over. So I can set a min replica count, I can set a max replica count, polling interval. There's a whole bunch of additional settings that I can set within the scaled object definition that are worth taking a look at. The trigger in this case is going to be RabbitMQ. I'm going to use the HTTP protocol, as I mentioned before. The queue name that we're looking at is orders, and we'll actually see that queue a little bit later. And I'm saying, hey, once the queue depth gets beyond 10, then you should trigger a scaler, okay, or a scale. And then finally, the auth RabbitMQ connection. All right, so that's the scaler. All right, so let's grab this. We're just going to apply it. All right, cool. So that should be good to go. If I do kubectl get scaled object for the pets namespace, I should see it there. Okay, kubectl get HPA. And there's my HPA. In fact, if we want, we can kind of play around with this. Let's watch kubectl get HPA for namespace pets. And I'm going to do k delete. Again, sorry for the K there. Dash F virtual worker. Boom. HPA is gone, right? If I go back and apply that again. And there we go. We can see the scaled object get created again there. All right. So now let's test the scaling. So right now, if I open up another window here, I'll split, and I did show down here the commands. But there's a question, maybe someone can share the link in the chat. There's a question of where this is. So this is the azure-examples.github.io/AKS labs. That should take you into it, and then you navigate into docs and operations, but maybe someone can post that into the chat as well. All right, so what I'm gonna do is I'm gonna do this watch, kind of skipping around a little bit, but you can kind of run through it yourself. If I do a watch, I'm watching the deployment down here. That looks good. Okay, so all my pods are running. If I minimize this top window, I can see right now I have one virtual worker, one virtual customer. So what we're gonna do is we're gonna scale up the number of virtual customers. I'm gonna scale it up to 4. And for the purpose of speeding things up, I might actually take it up to 8. 4 will work, but just to really kind of speed things up and make sure that we're seeing some action quick. All right. So I can see my 8 virtual customers spinning up here. Okay. Now I've provided a couple different commands you can use to watch things. So obviously there's watching the deployments in pods, but if you want to see specifically what KEDA is doing, we did share, you can actually watch the Kubernetes event stream and specifically target that HPA. There's a lot of different ways you could do this, but this is one quick way to do that. So let's fire this up. And we should be able to see if there are any events triggered. So if KEDA comes in and says, hey, I need to make a change to the number of instances of the virtual worker based on the scaled object, we would see that come through here. Another command, a couple of commands we shared in here actually, is you can exec into the pod here and take a look at the queues. So let me split this one again. And let's take a look here. So this is actually going to exec into the RabbitMQ pod and then take a look at the queues, and we should see the queue depth. So now we're 8 orders. If I keep watching that, you should see the number of orders change. One more that I also provided in here, if you prefer, and these are all doing the same thing. So this is really just kind of showing a couple different ways you can take a look at RabbitMQ. You can also port forward. Oops, see, actually, you saw right up here at the top now, we did get a new instance, so it's scaling up to 2. So if I minimize this a little bit more, let's see if we do this. That's in the wrong window. If I go down here, let's actually cancel this. Let's move this up. We should be able to see now we have 2 virtual workers. Okay. Before I jump on to the next thing, let me just show you this last part of how to look at the RabbitMQ queue depth. So if I do a port forward for that RabbitMQ HTTP endpoint, I can then also run a curl against it. So I'm effectively just going to curl the RabbitMQ orders queue. I'm going to pipe that into JQ. So again, this goes back to one of those optional commands. You don't have to do this, but it kind of pretties it up a little bit. And then I'm going to grab the queue status. So if I open this here, oh, it did this copy paste issue. When I copy and paste, it puts this extra slash in there. Take the slash out, should be good. There. So queue depth is 16. So based on that, I would expect that we're going to see another scale up here. So if I take a look at the scaled objects, we should see that go up to 3 shortly. But we can kind of keep moving. That'll happen on its own. But good to see that KEDA is doing its thing. So we can tell now that we've created our scaled object. We've kept an eye on that queue depth, and we can see that we're actually getting orders through. Sorry, we're getting orders through, and then we're triggering the virtual workers to pick up and start to scale up based on the depth of that queue. All right. Take a quick look at the chat here. All right. So for those who kind of joined a little bit late, just to kind of recap what we're going through here is this workshop. So let me zoom back out here. The AKS Labs workshops. And actually, we have a tiny URL as well for those who missed it, tinyurl.com/aks-keda-nap. Sorry, I didn't show that earlier, but I assume someone also posted in the chat. Tons of really great content in these workshops, networking, security. Specifically, what we're looking at is under the operations workshop, this scaling with KEDA and Karpenter. Okay, so you can go take a look at that. All right. Saw some responses. Thank you, Diego and Jim for helping respond on these. All right. So with that, KEDA is amazing. Definitely take a look at it. Take a look at the scalars that it provides. But now let's jump into the Node Auto Provisioner side of things. Okay. So first of all, what is Node Auto Provisioner? So several years back, the team over at AWS created something called Karpenter. So it was really looking at cluster autoscaler and the way that we scale workloads, which traditionally from a scaling perspective, across the various cloud providers and just in general, we think of in terms of, hey, I have this node pool and I want to scale this node pool up and down, right? And the reality is that a node pool isn't really something that Kubernetes necessarily understands. It's kind of something that's been created by compute providers as a way to say, hey, look, this is our scaling mechanism. We scale node pools, or we scale this in the Azure side. It would be a virtual machine scale set, and we say, okay, well, a virtual machine scale set is a node pool, okay? And it just makes it easier for us to think in those terms. But if you really look at it, there's no real concept in kind of out of the box Kubernetes of a node pool. We just label nodes and say, yeah, this node pool label is on this node, so it's part of that node pool. And there's a lot of things we do around that. The cluster autoscaler really just looked at things like, hey, do I have pods that are in a pending state? Okay, if I have pods that are in a pending state because there's not enough compute, let's scale up the compute. And it was able to do some different kind of choices around what type of scaling, like least waste and things like that. So you can go look at the cluster autoscaler documentation for what those were, but it was fairly limited in what it could look at. You couldn't necessarily say, hey, create an entirely new node pool of this machine type, or hey, take a look at what my costs are, look at the cost API and do scaling based on that. So, if you want to have your cluster optimize its cost using an autoscaler, that wasn't really something that cluster autoscaler was able to do. So Karpenter came in and said, hey, look, let's add some different abilities around this. Let's create a specification that allows you to have a more advanced set of controls around what that scaling looks like. So Karpenter laid out that specification, and then the cloud providers created their own implementations of it. So if I take a look here at the Karpenter project, Karpenter's really, again, it's a specification. The implementations of Karpenter come from the people who own the compute, the companies that own, or the individuals that own the way that the actual compute gets scheduled, right? So from an Azure perspective, we're creating virtual machine scale sets. So we need an Azure provider for Karpenter for this to work. Okay, in fact, if you look at the links right here, we do have that as well. You can go and actually dig in and take a look at this Karpenter provider for Azure, how it works, log issues with it if you see something there, and give that a go. All right, so using Node Auto Provisioner. So first of all, we enabled Node Auto Provisioner. So if I kind of scroll back up to the top here for those who joined late, when we created our AKS cluster, we specified Node Provisioning Mode Auto. So enable KEDA was for KEDA. Node Provisioning Mode Auto is for enabling Karpenter, which we call from a product perspective, an AKS product perspective, Node Auto Provision. You also hear us refer to as NAP. So if you hear NAP, we're talking about Node Auto Provisioner. All right. So back down here on Node Auto Provisioner, let's, first of all, what we're going to try to do here is if I jump over here and look at, let's cancel this. Should exit here, clear the screen here, clean things up a little bit. If I do a kubectl get pods hats and do a -oy to see what nodes things are running on. And sorry, this is a little bit messy view, but you can see that this is all running on node pool 1. Okay, so node pool 1 is our default Kubernetes node pool, right? So when I created this cluster, I didn't create a separation of system pools or user pools, so that's something you generally should do. So if you go take a look at the AKS best practices documents, generally when you're deploying a cluster, you would have a system pool, which our default node pool is the system pool. And then you would create user pools where your application workloads would run. And in fact, you can see that if I do a kubectl get nodes, let me grab this and do a kubectl describe node. If I scroll up and look at the labels when I'm describing this node, we should see it labeled as system. There you go, node system. Great. So it's labeled as a system pool, but what does that actually mean? Because if I look down here, there actually aren't any taints applied. So I'm not blocking anything from being deployed to this cluster. I've just labeled it as system, okay? AKS does that on purpose because AKS says like, hey, look, if you want to restrict, sorry for the background noise, if you want to restrict workloads that are running on the system node pool, then you should choose to do that. We're not going to do that. We're not going to force that upon you, but it is a best practice. So it's something you should definitely take a look at. So the way that you would do that is you get the node pool name, which we know it's node pool 1, but let's go ahead and grab it anyway. So I'm going to run this set of commands here just to grab the node pool name. If I echo that out once it's done, just to be sure, it should say node pool 1. There, node pool 1. Great. And then what we're going to do is we're going to do a node pool update. Okay. But we're going to apply a taint on it. And the taint we're going to apply is pretty aggressive. So critical add-ons only is the taint that AKS uses to define, hey, this is a system pool, only run critical add-ons on it. And all of the AKS system resources that get deployed tolerate the critical add-ons only taint. So you're not going to mess up the AKS workloads, the system pool workloads, by applying this taint. What we are going to mess up, though, is our application, because our application does not have a toleration for this taint. And we're going to go fairly aggressive with it. Generally, you would do a no schedule, which basically says, hey, don't schedule any workloads to this node pool that don't have the toleration. In this case, we're going to say no execute, which says, hey, violently remove any pods that are running. So we can actually watch that. I'm going to split this screen really quick, sorry. And let's down here run a watch. I'm going to do watch kubectl, get pods for the pets namespace, do -o wide again. Okay. And then up here, I'm going to run that update. And what we should see is once that update's applied, once that taint is applied on the nodes, all of these pods are going to get evicted down here. So you can see these all get terminated from node pool 1 because they are no longer permitted to run on node pool 1. All right, while that's running, I'll take a look at the chat and see what I've missed here. How can cost be managed for the cluster if we use Karpenter autoscaling? Yeah, so one of the capabilities of node auto provisioner through Karpenter is a awareness of the cost API for Azure. So it will look at the cost of different machine types and do optimization of your node pools based on cost. And you can take a look at the docs around that. You can also look at in the lab URL, there's the link to the Azure provider for Karpenter. So, okay. So you can see those pods were terminated. Let me actually expand this a little bit. I'm going to do get nodes as well. So we can watch the nodes as they're running. So you can still see we only have 3 nodes here. All right, so let me jump back over. We do have in the doc, similar to the KEDA side, we do have an events watch. So we can take a look at the events that are coming through. Now that that update has happened, I can watch the events. Okay. So you can see here that effectively Karpenter went in and said, hey, these pods need to be scheduled somewhere. And it looked at some of the built-in configurations that we provide, which I'll show really quickly now. If I look at node claims, so what is a node claim? kubectl get node claim. Okay, so the node claim, effectively, if you're familiar with kind of persistent volumes and persistent volume claims, think of it in the same terms. A node claim is essentially saying, hey, this is the node that we want provision. This is the node that's going to exist, right? And it scheduled the pod to that node claim. In fact, you can see here, default S5QW9, a node was just created by Karpenter with that on there. If I go back and let's watch that, but again, you can see that pods should schedule on. So it goes through all the pods for us and says, yeah, this pod should get scheduled on this node claim. You can see those are starting to create right now. All right, so I'm gonna kill this and let's take a look a little bit deeper at that node claim really quick. So I'm gonna take a look at the node claim again. Let's do a describe on the node claim. So we get node claim. Oops, let me output that as YAML. So you can see this node claim has a bunch of information in here. So it has, if I scroll from the top, let's see, it has a node class reference. Okay, so let's take a look at what a node class is. We'll play around with that a little bit. But it has a bunch of requirements. So hey, the node pool should be called default. It has the OS defined as Linux. Okay, so let's create a Linux node pool. It has a SKU family. So from an Azure perspective, you might be familiar with D series, E series, all these different things, right? So it specifies the SKU family in there. An on-demand node, it specifies the CPU architecture is AMD 64. And then it actually lists out all of the machine types. So these are the machine types that are available in the target region that I'm going to. So it went up and hit the API and said, yeah, what are the D series machines that I can schedule on? Okay, so that's the node claim. So we talked about the node class. Let's do kubectl get node class. Oops, sorry, it's AKS node class. There we go. So here I can see there's a couple different node classes in here. There's the default, which ours was called default. If you look at that node claims, this is probably the one that we're looking at. kubectl get node AKS node class. I'll put YAML. Okay. So this all looks pretty familiar. This is going to look very similar to what we had before. If I take a look at this, oh, sorry, this is the node class. So this is not the node pool, which we'll look at in a second. But the important part of the node class is right here. Right, so this is the spec for the node class. The node class is saying, hey, use an Ubuntu image. Here's the OS disk size that you should use. So obviously you can think in terms of if I'm trying to modify the machine type configuration, what can I, what should I be using? What OS version should I be using? What should I be setting for the OS disk and all that? Okay, I see some things in the chat. Having user mode pool where I have applied taints, does the new node, the provision have the same taints? No, so if you have a user mode pool, so you apply taints in AKS at the node pool level. So if you look at that update command, oops, I think I lost my terminal. Let me bring that back up. Let's bring a terminal back up here. Sorry about that. All right, so you take a look at this AKS update command. I ran it at the node pool level. So you wouldn't apply taints directly through kubectl, and any new nodes that are created within that node pool are going to get that taint. But I did not apply taints for anything on the node auto provisioner side. Like you can in node auto provisioner define taints that should be applied on nodes as they're provisioned, but we didn't do that. So there were no taints on the new nodes that were created. In fact, if we do a kubectl get nodes and take a look at this node that was created, and I scroll up here for taints, there are no taints applied on here. But there are, I could have applied those through a node auto provisioner, I just didn't. Okay, what about reservations in NAP, how to reserve nodes there? So there are capabilities. You can take a look at the docs around if you're doing capacity reservations. There's details about how that works. So you can use, reserved capacity with node auto provisioner as well. All right. So let's get back to the guide here. All right. So we talked about node claims. We talked about the node class. What we didn't look at was the node pool. So Karpenter, again, I mentioned that Kubernetes itself has no concept of a node pool, but Karpenter brings the concept of a node pool. So I can do a kubectl describe node pool default. That should work, right? Yeah, there we go. Okay. So this is the node pool, the default out-of-the-box node pool that we provide. There's also a system surge pool. You can imagine what that's for, system resources. But this is the default one that will get applied. So you can see here, what are some of the configurations you want on there? What's the specification? Here's the node class that it used, right? So that default node class, which triggered an Ubuntu node, right, with an OS disk size of 128. We saw all these things, the AMD architecture, Linux is the OS, on-demand type, the SKU family, all of this stuff effectively drove. There's also the startup taints. So again, you can apply these things. You can look at the Azure provider for node auto provisioning. You can take a look at that, the Karpenter provider, to see what some of these details are that you can configure. So let's go and actually take a look. Let me look at the system search pool as well. Why not? Okay. So system search looks pretty much the same with the exception of there's some additional labels that go on there. All right, so you can see the metadata labels. You can see that it has the system mode on there as well. Okay. All right, so we're going to create our own node profile, and then we'll look at node class. So from the node profile side, you can see a couple of things here that are interesting. I'll come back to the weight in a second. But what I'm going to do is specify the default node class. So I'm going to keep it that way, but I'm going to switch it from AMD 64 to ARM 64. So, for the lab purposes, we're thinking, hey, what if we're trying to minimize our energy footprint a bit? So we're going to switch things from AMD to ARM for whatever reasons you may choose to do that, right? So what if we wanted to do that? Just simple change there. Okay, what if, we want to make sure that it's Linux, we want to make sure it's on demand, but how do I override the default pool, right? So there is a weight mechanism that Karpenter provides. So you can effectively, the default weight is 0. So the default node pool and the system search node pool, their default weight is 0, but you can go in and increase a weight. It goes up to potentially 100. So you can say, hey, look, this is the provider, this is the node pool definition that we want the most. But hey, if that doesn't fit, then we can jump down to this next one. All right, so let me run this and I'll jump in and take a look at the chat really quick. Let's clear this. I'm going to fire that off. Okay, so if I do get node pool, as you see, there's my new ARM pool created, and let's watch kubectl get nodes and pods for the pets namespace, and we're going to do a -o wide. So before I do that, let me copy this. I'm going to scale back down because I think it might be a little bit easier to read. I'm going to scale the replicas here back down to, so I should scale to 4. Now let's run this command. Okay. So we should see this a little bit easier to read once that's done. And then also down the bottom here, why don't I go back? I think we showed this command here. I'm going to watch Karpenter again. So again, looking at the event stream that Kubernetes provides, let's watch what happens. What we should see is at some point it's going to switch down to, hey, we actually want an ARM node running because it has a higher priority, and then you should see these things start to switch over to that ARM node. Minimize this a bit and jump back over and take a look at the chat. If I have auto provision on both system and user pool, does it scale both the node pools separately? Yeah, so effectively it will scale them individually. Both the system pool, so you think of node auto provisioners doesn't necessarily get bound to a specific node pool. So node auto provisioner is just looking at the cluster in general and scaling based on that. Okay, so here we can see really quick, there's our ARM node that came online. So if we went and took a look at node classes, we would see that there is, if we looked at the node claims, we should see that there's a new node claim that was created. And then we'd also see this is being scaled up. We can see that it immediately evicted the pods once that node was in a ready state. If you kind of scroll through here, we can see that there's a node. It was nominated, the node was nominated. Once it was ready to go, it evicted all those pods from the existing node and moved them over to our new ARM-based node. Now you can see up here, all of our workloads are running on the ARM pool. So all I had to do was apply, I didn't touch the workloads at all. It's important to note that I didn't apply anything like a pod disruption budget. Obviously, if you're doing this in the real world, you're going to have workloads that you want to keep alive during these types of operations. So you want to make sure you have a pod disruption budget, and all of that will be supported as well. So just like if you're doing a Kubernetes upgrade on your AKS cluster, you want to make sure you have those pod disruption budgets so that you're not going to kill your workload while it's running. Same thing with the node auto provisioning. You want to make sure you have pod disruption budget So as it goes and says, hey, I didn't move this pod from this node over to this new node, it'll make sure it does that within the bounds of your pod disruption budget. You will see potentially a second node come online. That's just node auto provisioner saying, hey, I might need this extra capacity. And then it realizes, okay, I didn't need this, and it will delete it within a couple minutes. You'll see that node disappear. Okay. So we have about 10 minutes left, which is perfect because I'm going to jump down to the last part here, which is we're going to change up and do a node class. So imagine that we've decided instead of using Ubuntu, we have a new enterprise requirement to use Azure Linux. For those of you who aren't familiar, Azure Linux is the Microsoft Linux distro. It's a great solution because it allows us to have full control over CVE patching and things like that, right? Like we don't have the ability to force patches onto Canonical for Ubuntu. So having Azure Linux lets us kind of maintain that cadence, get things out faster. It's also container optimized Linux. So if you haven't looked at Azure Linux, it's definitely worth taking a look. But what we're going to do here is add a new profile. So we're going to have a node class that specifies that the image family should be Azure Linux. And then we're going to take pretty much the exact same node pool profile, but we're going to change the node class definition to say, hey, use our Azure Linux, and then we'll just apply that. And we should see a pretty similar behavior. So if I cancel this, let's go into our reactor namespace again, or our folder again. Let me run this one. Okay. And let's run that watch again. And we should see within a minute or so a new node come online. It's going to be an AKS ARM node. But if you look at the OS image on this side, it should say Azure Linux or CBL Mariner, I think is what you actually see. I'll take a look at the chat. Nothing new over there. All right. So you can see all that work that's happening here for the node claim creation. I'm going to take a look at this. We should say kubectl get node claim. Okay. So here's our new node claim that was created. If I take a look at that, let's see, we should see a different OS. All the way to the top. There we go. There it is. So our node class now is different. So this one should use Azure Linux. Let's go back and take a look at that Karpenter output. Oops. Hold on. Okay. There we go. So now we can see we have a not ready node. So it's just starting up. And we see that that's using CBL Mariner as the OS, which is Azure Linux, formerly known as Mariner Linux. And now we see the transition happening. The node is in a ready state, and we should start to see all of these nodes switching from GZ to 5Q. There we go. So now it's all going to this 5Q node pool. Now, one thing that's interesting to note is that part of the implementation of Node Auto Provisioner was the Node Auto Provisioner is not using VM scale sets anymore. It's doing VM instance-based deployments. So you can take a look at that. That was a new feature that was released close to the same time that Node Auto Provisioner was released. The node-based scaling. So if you do AKS node-based pool. Probably looking at the wrong one. Virtual machine pool, that's how I wanted. Virtual machine node pools. This is in preview as well. So effectively what's happening is that it's creating VM instances instead of VM scale sets for these deployments. And why that's interesting is that it allows you the ability to have more dynamic pool types. So you can still have node pools and say, hey, this is the node pool we're using for this workload. But you can say, okay, but this node pool has mixed types of SKUs. So it has D series, it has E series, maybe it has a mixture of GPU SKUs in there. So it allows you to kind of maintain the node pool concept, but that's a much more dynamic environment. You're not locked into VM scale sets for that. So that was kind of one of the crucial components of making node auto provisioner work the way that we wanted it to. So very cool feature and something you can use outside node auto provisioner as well, but it definitely kind of helps make things work really nicely here. So with that, I think we only got about 5 minutes left. So we're going to kind of wrap it up here. Hopefully, some of you got a chance to play around with this and give it a shot. You can go through, run this lab at any point. But at this point, you should have had a good understanding of, the fundamentals of Kubernetes Event-Driven Autoscaler, specifically through the managed add-on that AKS provides, and how you can use those different scalers that come out of the box. You can even create your own scaler and deploy that. So if there's a specific capability that you want to scale on, there's lots of good documentation in the Kubernetes docs, the KEDA docs, about how to create your own custom scalers and use those. So definitely worth taking a look at that. Contribute to the open source project. If there's bugs or if there's new features that you want in KEDA, definitely go take a look at that because it's a really awesome community. And then we jumped into Node Auto Provisioner. We talked about how the Karpenter project kind of enabled this concept of, new mechanisms for identifying, target node types that you want to scale with. So cost-based scaling, different SKU families and things like that you can use within Karpenter, and how the Azure provider for Karpenter enabled that specifically in the Azure ecosystem, and then the managed add-on took advantage of that for AKS. Now you can have node auto provisioning as a kind of managed capability in AKS. It's even provided, I believe, in AKS Automatic out of the box as well. So if you're looking at AKS Automatic, node auto provisioning is part of that. We dug into what node classes are, what node pool definitions are, and how they operate, how node claims, give you a view of what's happening with the nodes that are applying. And I think the coolest thing with all this is all these changes that we're making. I never touched my workload, right? The workload stayed static. It was just running. It just got moved around to different machine types. And assuming I put the right steps in to ensure that my running application didn't have any downtime, pod disruption budgets, things like that, really the end users would have had no idea that this was happening. But what I'm getting is more optimized compute, more cost-effective compute in the back end, really just by using Node Auto Provisioner. So hopefully that gave you kind of a good sense of those two capabilities. Hopefully you enjoyed the lab. Definitely go take a look at the workshops that are out there. Lots of really good content. Contribute. Let us know if there's labs that you'd like to see. We're going to be hopefully building out quite a bit more here. And yeah, hopefully everyone's staying cool and having a great beginning of summer. Thanks for hanging out with us. And yeah, can't we use Cast AI? So I don't know enough about Cast AI to comment on that, but I'll take a look and maybe try to respond to you in the chat. But thanks everybody for joining us today, and hope you had a good time. And yeah, it's great seeing you all. Have a great day.